Hello students. So up until last class we looked into the application of vector calculus in mechanics basically. So using the vector calculus you can be able to express things like velocity, acceleration in some vector notation. So today we will continue with those things, and we will see there are several other concepts like momentum, angular momentum, aerial velocity, or some equations of motion of some particle under some kind of law basically can also be expressed using the concepts of vector calculus. So today we will start with aerial velocity, and then we will move to momentum, and then we will try to write the equation of motion of some particles. So we will see how we can do that. So to begin with, let me give you a formal definition of the aerial velocity. So when I say aerial velocity, it basically means aerial velocity. So the aerial velocity, basically the aerial I need to correct the definitions. Spelling basically aerial, yes, A-R-E-A-L, velocity. So the aerial velocity of a point P about the point O, the origin of the reference system is the time rate of change, description or change, basically description of the vector area swept by the line OP. So what do we mean by it? So we basically mean that suppose we have a line, this is our reference line OX, and this is our given curve, and so this basically will be our point P. So this is our vector R, and this is our point, let us say Q, and this is R plus delta R, and this is our angle theta, and that is basically theta plus delta theta. And suppose here we have a tangent. So here we have a tangent. So this is actually N and V. So what it means is that the aerial velocity of a point P, so this is our point P about the point O, which is basically the origin for the reference system, is the time rate of description of the vector area. So this is basically the vector area in this direction. So this is our R, this is R plus delta R. So this is the vector area that is being swept out by the vector OP, and that is actually the description, the time rate description of the vector area is actually called as the aerial velocity. So how do we write in terms of the vector equation? So we start with let us say proof, basically. So a small proof. So we consider a general. So consider a general case of motion. So basically this particle P is moving along this curve. However, we assume that consider a general case of motion of the point P when its path is not necessarily a plane curve. All right. And now let P and Q be the two positions of the particle at the time t and t plus delta t, at the time t and t plus delta t, and let r and delta r plus delta r be their position vectors, all right. So, then if this area is delta A, so if this whole area is delta A, so if I call this area as delta A, so let me write, if delta A denotes the area of the triangle. So, since delta r is a very small arbitrary increment, so then in that case this OPQ is actually forming a triangle. So, it is not actually a curve, this PQ, it is basically considered as a line, because this increment is considered to be very small in a very small increment of time. So, delta t, delta r, they are considered in very small quantity. So, basically delta A is the area of the triangle OPQ, right. So, we know that the area of a triangle is given by 1 by 2 times 1 by 2 r, which is basically this vector, times or cross product with r plus delta r, right. And this is basically 1 by 2 r cross r plus 1 by 2 r cross delta r. So, since r cross r is 0 vector, so this is 0 vector plus this quantity. So, ultimately we have is 1 by 2 r cross product with delta r, all right. And now, if I define the, so the rate of change of, so the definition says the time rate of description of. So, the time rate of this change of this area of this description of the vector area will be, basically we have to take dA dt, delta A delta t, because that is what we are denoting the rate of change of the area swept by the vector OP. And just for the notation point of view, I think it's a good idea to take it as small delta A, just for the sake of notation. So, small delta A. So, we are basically in delta notation. So, delta this delta. So, I will also take it as small delta, all right. So, it's basically notation, but it makes the whole thing look nicer in a way. So, delta A by delta t is equals to, since delta t is a scalar, we can put this delta t here. So, delta r by delta t. Now, if I take delta t goes to 0, so proceeding with delta t going to 0, we will have a limit, this thing will actually reduce to, we don't have to write the limit, we can write simply as dA dt is equals to 1 by 2 r cross product with dr dt. So, that means the required, therefore the required aerial velocity, the required aerial velocity, which is basically the time rate. This dt is signifying the time rate of description of the area swept by the vector OP, right. So, this is basically the time rate of description. So, the aerial velocity is basically 1 by 2 r cross product with dr dt, and this is the required aerial velocity for this point P, whose position vector is given by vector r. All right. And similarly, we can calculate. So, here in my lecture note I have also calculated the moment basically. So, how do we calculate the moment? So, this proof is complete up to here. Let me also give you the moment. So, the moment, you may have studied these things in your physics course. So, the moment about O of the velocity vector say v. So, this is not the aerial velocity, this is the usual velocity vector v considered localized along the tangent line at P is by definition. So, the moment is basically a moment O, the moment about O. So, the moment of the particle about O of the velocity vector basically. So, the moment of the velocity vector considered as the localized along the tangent vector, and it is given by, so by definition it is given by r cross v, right, and its direction being at right angles or perpendicular, basically right angles to the plane of r and v. All right. So, it is actually at the right angle to the plane of r and v, and if we want, and if we consider this as the, so this is our n. So, if we consider this, so this as the perpendicular whose length is small p. So, if p is the length of the perpendicular O n, so I can write if small p is the length of the perpendicular O n to the tangent at P, then in that case, since r cross v is perpendicular to the plane of r and v, I can be able to write r cross v is parallel to that normal, and that is basically p times small p times small v. Small v is basically the magnitude of this velocity times n cap, because if r cross v is perpendicular to the plane of r and v, then it must be parallel to the normal in a way, and these are basically the scalars that signifies that it is basically a normal. All right. So, here we can, so here basically where v, small v is the speed of the particle or of the point P, of the point or particle, whatever you prefer, of the particle P, and n is the unit vector in the direction of normal to the plane of r and vector v. So, that means basically, so that means we can write, thus I can write r cross v is equals to p v n. So, that means from here I can write 2 times 1 by 2 r cross v p v n. So, this v is scalar and this is nothing but 2 times aerial velocity which is equals to p times v times n. So, this v is speed actually, and this shows that this is nothing but moment of v about O. So, this is actually our moment of v about O given by this formula, and that is actually twice the aerial velocity. So, this is one of the important formulas in this motion of a particle on a curve. And here we can see that with the help of vector calculus we can be able to show that the aerial velocity is half the moment of the velocity of the particle at the point velocity of the particle p about the point O or about the origin O. So, this is another important result that we can express using the vector calculus. It would also help if you have some knowledge of physics from your previous +2 level, just to make these things a little bit more clear. All right. Next is momentum and linear momentum, and then we will also write Newton's second law of motion using vector calculus, so, or vector notation basically. So, what do we mean by momentum? So, the definition you must remember, by momentum m, capital M, which is a vector of a moving particle at any time we mean the vector m times v, where m is the mass and v is the velocity of the particle, right. And in notation, or we write capital M is equals to small m times capital V. So, small m basically is the mass of the particle, and we mean the vector m v, where m is the mass of the particle and v is the velocity of the particle. So, for example, if you have, let us say, an iron ball, and if you just touch it on your hand, then it will not hurt you that much. So, suppose the weight of the iron ball is like 500 grams. So, if you just touch it with your hand, then it will not hurt your hand, but if you throw it that ball on your hand, then there is a strong possibility that it will hurt your hand. The thing is that since it got some velocity, the momentum is higher. So, when it is hitting, that is when you are feeling the blow actually. So, even though the mass is very huge, if the velocity is not high, then in that case the momentum will always be small. So, that is why when something hits us, or when someone get hit by something, then in that case that at that point momentum is high, basically because the velocity was high. So, momentum is directly proportional to the velocity, or it depends on the velocity basically. So, higher the velocity is, higher the momentum would be, and m is the mass, of course. Of course, it also depends on mass. So, if your mass is big and if the velocity is high, then the blow will be higher, and if the mass is small and velocity is high, then at that time also the blow will be higher, but it will not be as high as when you had a bigger mass. So, mass also plays an important role, but in case of momentum, I would say that velocity plays an important role. So, because velocity can increase and decrease, and based on that, for a given mass, the momentum can also increase or decrease. All right. Now, next we define the moment of a momentum. the moment of a momentum. You probably know all these things. It might be a recapitulation from your physics class, but I'm just writing the advantages of vector calculus here. So, if m be the momentum, if m be the momentum of a particle p, momentum of a particle, let us say p at any instant, and O be any point, then OP. So, then the vector OP cross M. So, this is not necessarily origin. So, this can be any arbitrary point. So, I could take Q, which or let's keep it as O. So, OP cross M is equals to vector H, because this is a vector, this is a vector. So, the cross product would definitely be a vector, is called the moment of momentum, or sometimes they are also called as angular momentum. Of the particle about O. All right. So, this is called the angular momentum of the particle about O. Now, so here basically, so here OP is the position vector of the point P about O. So, with respect to O, OP is the position vector, and in case O is the origin, in case O is the origin, then this can be written as vector R times capital M, which is basically vector R cross product with M times V. So, this can be written as M times R cross dr dt. So, V can be written as dr dt, and this is basically our angular momentum. So, the momentum cross product with dr dt, or M times R cross dr dt, is basically your angular momentum. So, if I go back to this formula where I had the aerial velocity, so basically aerial velocity and angular velocity. So, I can take 2 times aerial velocity. So, this is basically 2 times m times aerial velocity. So, that is basically our angular momentum. All right. And so, the thing is, and another thing is, angular momentum will be different for every point that we choose this O. If we choose O as a different vector point, then in that case this OP vector will change, and then of course our angular momentum will change. So, these are the small here and there details which you have to be careful about. So, here if we choose instead of O a different point, then in that case this angular momentum will change. So, yeah, this is our moment of momentum. The next topic is Newton's second law. Newton's second law of motion. So, you probably heard about there are three laws of motion, and when you say three laws of motion, it obviously means that we are talking about Newton's 3 laws of motion, because everything around us, they obey Newton's laws of motion. So, the first one we know that it's called law of inertia. So, if a body is in motion, then it will remain in the motion. If it is in rest, then it will remain in the rest, unless it is being compelled by some external force to change its state. And the second law is that the force is proportional to acceleration basically, and the third law is that to every action there is an equal and opposite reaction. So, these are the three basic laws which has a huge, which has huge application everywhere around you. So, anything that is moving, it has in one way or another some application of or direct application of Newton's laws of motion. So, basically all three of them are important, but today we will just derive or learn the second law of motion. So, the second law of motion says that the time rate, so the statement is the time rate of change, rate of change of momentum of a particle is proportional to the impressed force and takes place in the direction in which the force acts. All right. So, if P is the impressed force or if P is the applied force, then in that case let us call P, because if you are applying a force then it has a direction, because if you apply a force and expects the change to happen in this direction, that will not happen. So, when you apply the force in a certain direction, the change would also happen in that direction. So, the force is a vector quantity. So, it is always having a direction. So, that is why P is the force which is chosen as a vector, and it is directly proportional to the momentum. Momentum is a vector quantity because it involves acceleration, velocity, and m is basically the velocity, capital M v t. So, I can change this proportionality to a constant k times m dv dt. So, rate of change of velocity, and I can write this as k m a, where k is the constant, is a scalar constant, given constant of proportionality, m is the mass, and a is the acceleration. So, next if we choose the unit of force as 1 which produces in a unit mass, unit acceleration, then our k will be constant, then k will be 1. So, of course, it is constant, then k will be 1, and hence we will have P is equals to m times a. So, this is basically our Newton's second law of motion. So, that means force is equals to mass into acceleration, and this means that acceleration produced in a motion of a particle of a constant mass has the same direction as the force producing it. So, it will happen, the change will happen in the direction of the force, and this equation is called as the equation of motion of a particle. So, this is another application of vector calculus, or we saw that how with the help of vector calculus we can be able to write Newton's second law of motion. So, these are some of the applications of vector calculus in the applied mathematics or in mechanics. In the next class we will continue with that, and if time permits then we will move on to our next topic. So, I thank you for your attention today, and I will see you in the next class.